Hey everybody, this next video lesson is going to talk about a concept called spectrometry, and we're also going to take a look at a spectrometer. Now I realize that the title of this slide says spectroscopy, but it's actually spectrometry. Spectroscopy is the study of the electromagnetic spectrum, and we're not going to do that. We're going to be using a spectrometer to do spectrometry. I'd like to take a moment to introduce to you the instrument known as a spectrometer. Now, a spectrometer is a device that basically takes three parts: a source of light, a sample, and a detector. And then the output goes into a computer. So I guess that's the fourth part. But what you're looking for is passing light through a sample to figure out how much of the light that leaves the source either gets absorbed or transmitted by the detector on the other side. Before running your experiment, you tell the detector whether you want it to measure the absorbance or the transmittance, but you don't do both at the same time. It's one or the other. In most cases, I stick to the absorbed light. That's the one that we work with most often in chemistry. This instrument is used in order to figure out what the concentration of an unknown sample is inside the spectrometer. That calculation of concentration is many steps down the road here, but I'm going to take you through each one of those steps so that you can do this in practice in a lab upcoming in the future. Now, the spectrometer basically takes the light source as white light and then uses a prism to separate all the light into its different colors and passes each one of those different colors of light through the sample. The detector on the other side is either trying to figure out how much light gets through or how much light got absorbed by the sample. And that output data will then go into this computer. So in summary, the light leaves the light source, passes through a filter to narrow down a specific wavelength of light. The wavelength of light passes through the sample, and the detector tells you whether or not the light was absorbed or transmitted, and that input is then sent out to a computer. Now, the computer output is going to look like this graph you see right here. And in this graph, the spectrometer was scanning the same substance at different concentrations. As you can see, the different colored lines represent different concentrations of the substance. As you can see, it's I2. Now, I2 has a purple color. And so when we pass light through it, we're looking at how much light gets absorbed by that purple colored substance as we increase the concentration. A particular substance is going to absorb light, pass through it that is closest to its color. And so, as you can see, as the concentration goes up, you get more and more absorbance at or around the blue and purple range. Because this substance is purple in color in the first place, it will represent or show an increased absorbance as the concentration goes up, because it becomes more and more purple, and so you get more and more purple light absorbed. So let's use this blue line at 40 milligrams per liter. And the spectrometer starts out at measuring in the purple range of the electromagnetic spectrum. And you can see the absorbance is about 0.1. Now, absorbance doesn't have a unit necessarily with it. It just says it absorbs at 0.1. And as you get closer to blue, you can see that the light peak begins to increase, meaning there's increased absorbance at this wavelength. And then the spectrometer continues to scan at colors in the green and then orange and yellow, and then finally in the red side of the spectrum. As you can see over here, on the red side of the spectrum, we don't have much absorbance of the color. Absorbance and transmittance are opposites of one another. So if there is low absorbance in the red range, if we graphed our transmittance, you would have lots of peaks over here and not a lot down in the purple range. So you do this for 5 different trials at 5 different concentrations, and then you can graph each one of those on the same graph, like you can see right here. Now we're going to talk about how to take a proper reading using a spectrometer. So you're going to step up to the spectrometer. Now there's things called colorimeters as well. Now a colorimeter and a spectrometer basically do the same thing. They emit light, it's absorbed or transmitted through a sample and picked up by a detector. But a colorimeter you cannot scan the entire spectrum of color. A colorimeter only isolates specific colors. Usually a colorimeter has 3 or 4 options for 3 or 4 different colored lights that you want to emit from the light source. And so basically you eliminate this prism that separates the light into different colors. You go right to the source of the light, passes right through the sample and into the detector because the light color is been selected by the colorimeter. This is less expensive and obviously what you will be working with in our lab coming up in the future. Spectrometers are 10 times the price of a colorimeter, and we have 1 or 2 in the science department, but we have enough colorimeters for every lab group to have their own. And so a colorimeter does the same thing, but instead of showing you a spectrum of absorbances at different wavelengths, it will basically just read out a specific absorbance at a specific wavelength for you. But a colorimeter and a spectrometer, you would do the same steps. So the first thing you want to do is you put your sample into a cuvette. A cuvette is a little plastic or glass container that you put your sample into. Now you want to make sure that you use the exact same cuvette for every time you do a reading using the colorimeter or the spectrometer. Each cuvette is slightly different thickness of the glass or plastic. Some of them have different impurities inside the glass or the plastic. And so in order to ensure that you are eliminating all the different variables, you want to make sure that you use the same cuvette for all of your readings when you're doing a colorimeter or a spectrometer. Now inside the cuvette, you're going to put the liquid. The first reading you should do would be to always zero out or calibrate your colorimeter or spectrometer using the cuvette and the pure solvent. Now typically this is water that you use, and so you'd use distilled water to zero out or calibrate your spectrometer or colorimeter. And so you would just put a sample of water in, you'd hit the calibrate button, and then it will tell you, okay, your machine has been calibrated. Now you can begin putting your samples of different concentrations into your cuvette. Zeroing out ensures that the pure solvent and the glass of the cuvette are not factored into the absorbance, and that only the solute is what contributes to the absorbance in that reading. The third thing I want to talk about is before you take your reading, wipe off all of the fingerprints on the sides of the cuvette, because a fingerprint on the outside can actually cause some absorbance of the color. You want only the sample inside the cuvette to be what absorbs the color that passes through it, not the fingerprints or anything on the outside. Also, make sure that your cuvette is clean to start. Make sure that there's any chunks inside that are cleaned out, and if you can't get a clean one, ask your teacher and they should be able to find a cleaner version for you. Finally, if you're using a colorimeter specifically, you want to pick a wavelength of light that is as close to the color of your substance as possible, because substances that you're analyzing will absorb the colors that is closest to it, and it'll transmit the colors that are not similar to it. For example, if you have a purple liquid, then you want to use purple light or blue light in order to do your readings. You would not want to use the red light because all the red light would pass through and you would have very little absorbance of red light. Now a spectrometer eliminates the need to choose a specific color because it will scan on the entire electromagnetic spectrum for you, at least in the visible range. But a colorimeter, you have to choose a specific wavelength of light. So I'm going to erase this stuff and actually scroll up a little bit, give myself more room, because we're going to talk about next what to do with this information and how to get to that unknown concentration of a substance. I've taken the information from this graph up here, and I basically was looking at the maximum value of absorbance for each one of these curved lines. And I put into a data table and then graphed the concentration versus the maximum absorbance achieved by each one of these lines, as you can see in this graph and data table now. Now, if you had a colorimeter, you wouldn't need to look at a graph to figure out this data table. In fact, this data table would be something that you would fill in as you run your readings. You would know your concentrations that you're going to be doing, and you put in the first trial, and then you hit go, and it'll tell you an absorbance. and you write it in the data table. And then you would have your second trial and write that in the data table, and so on and so forth. Because I had a spectrometer readout like this, I had to generate this information from these maximum absorbance curves. Using Vernier's graphical analysis tool, once I put the numbers in, it automatically generated a graph for me. And then in the lower left-hand corner, you can choose to apply a curve fit, and it automatically chooses a linear fit. Notice that the concentration versus absorbance lies on a nearly perfect straight line. And that is really useful information for us, because now we can solve for an unknown concentration as long as we know that the solute substance is the same as the ones that we ran in our 5 trials. Now you probably asked yourself after Algebra 2, when am I ever going to use y equals mx plus b ever again in my life? Well, let me tell you that today is the day that you're going to do that, because we're going to use the data generated from this line and the equation of this line to apply something called Beer's law. Beer's law says that the absorbance, or capital A, is equal to A times B times C plus 0. But usually we just leave the plus 0 at the end. Where A, as I said, is the absorbance, capital A. Lowercase a represents a coefficient of the glass, of the cuvette. And so that number will always be constant because you use the same cuvette in each one of your trials. B is the length of the light path of your colorimeter or your spectrometer. So once again, you use the same colorimeter or the same spectrometer in each reading. And so A and B will always be constant. Now C is the concentration of the solution. Beer's law is set up to equal y equals mx plus b, where y is the absorbance, m is a combination of A times B together, where x is the concentration, and b is the y-intercept, but we said that's plus 0. Beer's law always has plus 0 as a y-intercept. So essentially, that the absorbance is proportional to the concentration in a linear fashion. So looking back at my graph up above, if you know the equation of the line for y equals mx plus b of your data set, the slope of this graph is the glass coefficient times the length of the light. And the two unknowns, y absorbance and x concentration, will then allow you to be able to figure out an unknown concentration if you know the absorbance of an unknown substance, as long as you use the same solute and solvent as you did in your 5 trials up above. So in my lab, I have ran my 5 trials, I've generated my line, I've got my equation for my line, and then you're going to be given a last sample, but you do not know the concentration of this sample. You know it contains the same solute and the same solvent as you did for your 5 trials up above. But let's just say, for example, the absorbance of that substance was maybe like 0.60. Now that is actually more than my largest example, but this can work to extrapolate as well. Let's say your absorbance was higher than one of your 5 trials, but that's okay because you know that this relationship is 100% linear. And so even if you go past your highest data point, you can trust that the concentration that you calculate is 100% correct. And so we know that the absorbance is 0.6. Now we apply the same slope and the same y-intercept, and then we can calculate and solve for x. So in my calculator, I took 0.60 and I added 0.003196 to that side to isolate x, and then I divided by 0.00415, and I got x to be equal to 145, and that's the concentration in milligrams per liter. And I would expect that to be larger than my largest trial from the one up above, which, as you can see just at the top of the page, was 100 milligrams per liter. And so this makes sense. Since the absorbance was higher than the highest absorbance, then the concentration must be higher than my highest concentration that I know. But you can say, because of Beer's law, that that right there is the concentration of your unknown sample. Here's a look at a problem that you might see on an AP test. In fact, I took this off of the practice AP tests found on the AP Classroom that had to do with spectrometry and Beer's law. There are questions in the multiple choice or in the FRQ section of the AP test that may have to deal with spectrometry or Beer's law. And here's an example. It says, using a spectrometer, a student measured the absorbance of 4 solutions of CuSO4 at a given wavelength. The data collected is in the table below. Which of the following is most likely explanation for the discrepant data in trial 4? Now, first of all, we need to decide, is the discrepant data in trial 4 too high of an absorbance or too low of an absorbance? Why don't you pause the video right now and try and figure out if you can come up with the correct answer. We know that concentration data and absorbance data are linear according to Beer's law. So if concentration goes up by a certain amount, then absorbance should go up proportionally. Now the first 2 trials, 0.025 to 0.05, that goes up by 0.025, but then it jumps in trial 3 to 0.05 difference in concentration. And so that difference between trial 1 to 2 and 2 to 3 is not a uniform amount, so I don't necessarily want to use those 3 trials to make my decision on whether or not trial 4 is a good one or not. But take a look at trial 2 to 3, it goes up by 0.05 molar, and then from 3 to 4 also goes up by 0.05 molar. And so these 3 trials are the ones that I'm going to focus on. Now it goes up from 0.05 to 0.10, and the change in absorbance is found by taking 0.520 and subtracting 0.268. And that difference is 0.252. Now, if that's the case, then when you go from 0.1 to 0.15, then you should increase by 0.252. So if you take 0.252 plus 0.252, you should get 0.772, but you see that your actual answer is 0.680. So the absorbance in trial 4 is too low. Then it should be 0.772, but it's 0.680. So let's go through the answer choices and figure out what effect each one of these would have on the concentration or absorbance. The first one, it says the solution was at a lower temperature than the solution in the other trials. Well, at first thought, temperature doesn't seem to affect concentration, and then I thought to myself, wait a minute, concentration or molarity is moles per liter, and volume is affected by temperature. When the temperature increases, the volume also increases. And molarity is affected by changes in temperature. If you take a substance that's maybe 1 molar at room temperature, but you increase the temperature, then the volume increases, keeping the amount of solute the same. And so technically, as temperature goes up, concentration goes down. Now if temperature goes down, concentration goes up. So in A, it said that the solution in trial 4 was lower. If it was, it would actually be higher than it should be, but it's actually lower than it should be. So we can toss out option A because this is opposite. This would result in a drop. This would result in an increase in concentration. Now part B, or option B, says the measurement was made using a different spectrophotometer that uses a cell with a longer path length. Now remember, Beer's law is A equals ABC. And as absorbance goes up, concentration goes up as long as A and B are held constant. Now, the path length would be longer, would mean that B, in fact, would be bigger than it is. And a bigger B would mean that when you multiply it times the concentration, the outcome would be a higher absorbance. And once again, we have a lower absorbance than what it should be. So again, part B, if that were the case, would increase the concentration, but we see an actual decrease in the concentration. Now let's take a look at part C. It says the solution was saturated and the flow of light through the solution was restricted. Now that right there is a definition of increased absorbance, but again, we witnessed a decrease in the absorbance, and so this also can't be correct. Now by process of elimination, the correct answer is D. But D is indeed correct. Take a look. It says the concentration of the solution was actually lower than 0.15. Now that would result in an absorbance lower than it should be. So that is the correct answer. Now just for you, I've got one more example of a type of question you'd see on a multiple choice test for the AP test. This one says to determine the number of moles of Cu in a sample of a mixture, the student measured the absorbance of the known concentrations of copper nitrate using the spectrophotometer. A cuvette filled with some of the solution produced the sample of mixtures was also tested. The data recorded by one of the students shows the table above. On the basis of the data provided, which of the following is possible error that the student made? So I look at the data, and the concentration increases by 0.025, then 0.05, and then by 0.1. So it seems to be escalating as you go down here. Then I notice that the absorbances go up, but then all of a sudden in this data point, they go down. And so that gives me a clue that something went wrong here in trial number 3. Now reading through the examples, the first one says, the copper nitrate from the sample of the mixture was not diluted properly. Now at first glance, I thought that was possibly the correct answer, and it still might be. So I'm just going to put that one on the shelf. We'll see if there's a different answer in here that could possibly explain why the absorbance jumps around here even though the concentration increases steadily. The spectrophotometer was calibrated with tap water instead of distilled water. Now that would definitely throw off your absorbance data, especially if you're trying to figure out what the unknown sample concentration is. But you're not worried about what the unknown sample concentration is necessarily. You're trying to figure out why it goes up and then goes back down again, even though the concentration continues to go up. Furthermore, using tap water to zero out your spectrometer would actually affect all of your absorbance data equally. And so that wouldn't necessarily explain the discrepancy in values between 2 and 3 here. C says the student labeled the cuvettes incorrectly, reversing the labels of the 2 solutions of known concentrations. Now that might also possibly be a correct answer, but I need to check the math to make sure that the absorbances are going up in a way that is consistent with the increase in concentration. So right now I've narrowed my answers down to possibly A or possibly C. It says the spectrophotometer was originally set to an inappropriate wavelength, causing the absorbance to vary unpredictably. Now this one would affect all of the samples, and so even if it was set to an inappropriate wavelength, they would all be inappropriate equally. And so that doesn't seem to explain why these 2 numbers don't follow the pattern. So either the dilution was not done properly or the labels will be reversed. I'm going to take a look and see if I put 0.117 and 0.235 in switch places, and then I take a look at the difference in absorbance and see if it is proportional to the difference in concentration. If that is the case, then C is the correct answer. If that's not the case, then A must be the correct answer. I took a look at the absorbance numbers, and I took a look at the first 2 trials. I took 0.117 and subtracted 0.059, and I got 0.058. So an increase of 0.025 concentration results in an absorbance jump of 0.058. Now the next one goes up by 0.05, so it's double the concentration jump, so I'd expect to double the absorbance jump. So I took 0.235 and subtract 0.117, and I got 0.118, which is in fact a double absorbance jump from 1 to 2 to 2 to 3. Just to make sure that I did it right, I did another one between 3 and 4, and once again it's a double jump. So it goes from 0.235 to 0.468, and the difference between those is 0.233. So once again, the absorbance doubled when I doubled the concentration. This is consistent with what Beer's law says, which says that as you increase the concentration, the absorbance increases proportionally. And so the correct answer here must be that the student labeled the cuvettes incorrectly and accidentally flip-flopped them. Well, that takes care of this video lesson. Thanks for watching.